Hello students. So, now coming to the next video lecture of module 2 of data mining and data warehousing. So, in this video lecture we are going to discuss indexing OLAP data. So, there are two methods for indexing OLAP data. One is bitmap indexing and second one is Jian indexing. So, indexing OLAP data, there are two methods, one is Jian index and the bitmap index. So, why indexing is required? So, why indexing of OLAP data is required? To facilitate efficient data accessing, most data warehouse systems support index structure and materialized views using cubites. General methods to select cubite for materialization that we have discussed in the previous section, that which cubites to be selected for materialization, whether we need to go for full materialization or partial materialization. Even if you want to go for partial materialization, what are the things that we need to consider? So, here we will study how to index OLAP data by bitmap indexing and Jian indexing. So, bitmap indexing method is a popular in OLAP product because it allows quick searching in the data cube. So, you have arranged a multi-dimensional data in a data cube of a data warehouse. So, whenever you put a query to access the data from a data cube, what we expect? We expect a very less response time or very quick response from the data cube. That is, whenever I put a query to access the data, I need to get a very fast response. So, how I need to do that? So, if I want to access a data from a huge amount of data, I need to first index them, like your books are being indexed. So, if I want to search for any particular topic in a book, I do not search page by page, I go to the content of the book, I go to the index, I search for the particular topic, I go to that particular page number and I access the data. Similarly, in a data warehouse where a huge amount of data is present, so here also indexing is required, so that whenever I search for a particular data, I will go to that particular, I will search for the index and I from that index I will find the address of the data and I will directly access it. So, bitmap indexing is one of the popular product in the OLAP because it allows quick searching in the data cube. So, bitmap index is an alternative representation of record ID RID. So, instead of representing each data by a ID called as record ID, so here we are replacing that record ID by a bitmap index. In the bitmap index, for a given attribute there is a distinct bit vector. For every data, for every attribute there will be a distinct bit vector that we call as B of V for each value V in the attribute domain. For every attribute we will be having a vectored value that is represented by B of V, where value of V is the attributes domain. So, if a given attribute domain consisting of n values, then n bits are needed for each entry in the bitmap index, means there will be n bit vectors. Okay, if there are n values and these n values are represented by n bit vectors. If the attribute has the value V for a given row in the data table. Now consider your data is arranged in the form of rows and columns. If the attribute has a value for v for a given row in the data table, then bit representing that value is set to 1 in the corresponding row of the bitmap index, and all other bits for that row are set to 0. Means if a particular attribute is present or it is having a value v for a given row in the data table, then its value is represented by 1. 1 means the data is present in the data cube, and if it is not present, then all the values are set to 0. So, each value in the column has a bit vector, that is bit of is fast. So, each value in the column has a bit vector that represents whether that particular data is present or no. The length of the bit vector, what is the length of the bit vector? That is the records in the base table. The ith bit is set if the ith row of the base table has the value for indexed column. Now, if ith bit of ith row will be set equal to 1 only if the base table has the value for indexed column, and this is not suitable for high cardinality domains. High values are not preferred. So, let us take an example indexing OLAP data using bitmap indices. So, the figure here 4.15 gives an example of all electronics data warehouse. So, in this case, suppose the dimension item at the top level has 4 values representing the item types. Okay, so here one is the base table, another is item bitmap index table and city bitmap index table. So, the base table contains item and city, and the bitmap index table contains the item contains either the home electronics, H represents home electronics, C for computers, P for phones and S for security, and city bitmap index table contains a city Vancouver and Toronto. Okay, so now let us take the item at the top level has 4 values representing item types. One is home entertainment, computers, phones and security. Each value, for example, computer is represented by a bit vector in the bitmap index table. Suppose that the cube is stored as a relational table with 10,000 or 1 lakh rows, because the domain of item consisting of 4 values, the bitmax table requires 4 bit vectors, each with 1 lakh bits. So, here in this figure shows a base table that contains the dimension item and city, and it is mapping to the bitmax table for each of the dimensions. So, now take the base table. R1 is the record ID. First record ID says that the item home entertainment is sold in the city Vancouver, computers sold in the city Vancouver, phones sold in the city Vancouver, and the security electronics are sold in the Vancouver. Similarly, home electronics, computers, phones and the security in Toronto. Now, we will see one by one. During the record ID 1, home entertainment is sold. During record ID 2, computers are sold. Record ID 3, phones are sold. Record ID 4, security things are sold. And R5 again home entertainment, then R6 computers, R7 phones and R8 is the security. Then city, Vancouver and Toronto, and first 4 transactions R1, R2, R3 and R3 are the 4 records contains the data related to the city Vancouver, and next R5 to R8 contains the records related to the Toronto. So, whenever you want to access the data related to the city Vancouver, you need to reference or you need to go for the record ID R1, R2 and R3, and if it is 1, then it means that a particular item has been sold, and if it is 0, then particular item is not sold. Now, if you take the next 4, if you want the if you search for R2, if you want to search for the sales of electronics in the city Toronto, then you search for record number of R5 to R8, where we will give you the records related to the sales with respect to the home entertainment, computers, phones or security. So, this is bitmap indexing. Bitmap index 1, this is bitmap index 1 vector, which what it represents? It represents a particular item has been sold during a particular record in a particular city. R1 Vancouver, okay, some of the electronic item is sold during 4 transactions. During R1 in Vancouver, some electronics is sold. During R1, what is sold? Home electronics. During R2, what is sold? Computer is sold. During R3, phones are sold. During R4, security electronics are being sold. So, if you want to search, now if you want to search for Vancouver record during the record ID during transaction and in the city Vancouver, what is being sold? Now, you will directly find out that home electronics are being sold or home entertainment things are sold. So, base table also R1, okay, directly the city Vancouver, some home entertainment items are sold. During R2 in a city Vancouver, computers are sold. During R6 in Toronto, computers are sold. During R8 in Toronto, security systems are sold. So, this is how a bitmap indexing will be able to access the data directly. So, the bitmap indexing at advantages compared to the hash tree and tree indices, it is more better. It is especially useful for low cardinality domains because comparison, join and aggregate operations are then reduced to bit arithmetic. Okay, so, this is useful for low cardinality domains. Why? Because comparison, join and aggregation operations are then reduced to bit arithmetic, which substantially reduces the processing time. Bitmapping indexing leads to significant reduction in space and an input and output operation. Very less amount of space is required because every transaction is represented by either 1 bit. It is represented by only 1 bit. Bitmap indexing, what? It requires less memory space and less space for input and output operations, since a string of characters can be just represented by a single bit. So, here string of characters, now here we are not using any characters over here, we are either using 0 or 1. So, for these reasons it requires very less amount of space for both space and for input and output operations. So, if you want to apply this for high cardinality domains, then the button can be adapted using compression techniques. Now, coming to the next method, the join indexing method. The join indexing methods gain popularity from its use in relational database query processing. So, join based indexing method is used in relational database query processing. Traditional indexing maps the value in a given column to a list of rows having that value. In contrast, join index registers the joinable rows of 2 relations from a relational database. So, now here join index, what it does, it registers the joinable rows of 2 relations to form a relational database. So, now if the 2 rows are having some part of relations between them, then that can be joined to form a relational database. So, if a data warehouse, join index relates the value of a dimension of a star schema to rows in a fact table. For example, sales and 2 dimensions. Now, you can take a fact table with respect to sales with 2 dimensions, city and product. This can be combined, which will give you only one data related to a sales both with respect to city and product. A joint index on city maintained for each distinct city list of RIDs, that is the RIDs of the tuples recording the sales in the city. A joint index for every on city maintains for each distinct city. We will be maintaining RID, that is reference ID of the tuples recording the sales in a particular city. So, the advantage over here is joint index or joint indices can span multiple domains. For example, if two relations, if you take one reference ID RID of A and RID of D. So, this the attributes here, we have two attributes A and B, then the joint index record can contain per pair RID and SID, where RID and SID are record identifiers from the R and S relations. You have RID of A and S, B is equal to SID. So, now where RID and SID are the records identifier from the S and R relations respectively. Hence, the joint index records can identify joinable tables without performing costly join operations. Joint indexing is especially useful for maintaining relationship between a foreign key and its matching primary key from a joinable relations. The star schema model of a data warehouse makes joint indexing attractive for cross table search, because the linkages between the fact table and its corresponding dimension table comprise the fact table's foreign key and dimension table's primary key. So, joint indexing also maintains relationship between the attribute values of a dimensions, example within a dimension table, and the corresponding rows in the fact table. Joint index may span multiple dimensions to form composite joint indices. We can use joint indices to identify subcubes that are of interest. Consider an example of 4.16. So, here again we have defined a star schema for all electronic for sales star. So, here we are using the linkages. So, here we are using a star schema. The figure shows 4.16 shows the linkages between a sales fact table and the location and item dimension table. So, now sales star, what are the dimensions taken? Time, item, branch and location, and we also want dollars sold is equal to sum sales in dollars, the total amount of sales in dollars. An example of joint indexing relationship between the fact table and the location and item dimension table is what it is shown in the figure. Okay, now what is done here? So, location is the main street I am taking. So, now sales. So, transaction 57, transaction 238 and transaction 459 and transaction 884, all these 4 transactions which has happened in the location of main street have sold the item Sony TV. What does it mean? Means here all the transactions which have sold Sony TV, we are not maintaining a separate table for that. All the transactions are mapped to a particular item called as Sony TV, which is different than bitmap indexing. Okay, so now what is here? We have taken only one location is only one thing, and item is only one part, and sales, all the sales which have happened in a particular location, what sales has been done? Sony TV, make it on one side. Okay, so now here joint index table for location sales, location main street, sales key T57 T238 and T884. Join index table for sales. So, item Sony TV. So, what are the sales key? T57 and T49. Now, join index table linking location and item to the sales, location mainstream, item is Sony TV, sales key is 257. So, here join index table is based on the linkages between the sales of a fact table and the location and item dimensions table. So, now here everything, so all the things which are having a common part. So, here the transaction T57 to T238, T459 and T884, all these are having a common thing, what? A Sony TV. Now, that is grouped together. So, that is nothing but joining or linking between the different transactions. That is all regarding the join indexing. Next, coming to the efficient processing of OLAP queries. The purpose of materializing cubites. Now, materialization what? Materialization is before only computing values of the cubites. So, the purpose of materializing qubit and constructing OLAP index structure is to speed up the query processing. Why we are going for all these things? Why we are materializing the qubit? Why we are using either bitmap indexing or join indexing? What we expect is only one thing, to speed up query processing in a data cube. We want, as soon as the query is put to the data warehouse, immediately I want the result. Given materialized views, query processing should proceed as follows. First one is determine which operation should be performed on the available qubit. What I have to do? Which operation should I have to perform on a qubit? So, whenever a query comes, whenever an OLAP query comes to a data warehouse or a data cube, what should I do to what I have to do first? The first thing is determine which operation should be performed first on the available qubit. Now, what I have to do? This involves transforming any selection, projection or roll up or drill down operation. What I have to do? Whether I need to perform transformation, whether I need to go for projection, whether I need to go for roll up or I need to go for drill down operation specified in query into corresponding SQL or OLAP operation. Consider, for example, transform, drill and roll etc. into corresponding SQL and OLAP queries. Example, dice is equal to selection plus projection. For example, slicing and dicing a data cube may corresponding to selection or projection operation on a materialized qubit, that is dice is equal to selection of a qubit then plus projection. And second, what I have to do? Determine to which materialized qubit the relevant operation should be applied. Which operation I have to apply and to which qubit? To which materialized qubit the relevant operation should be applied. This involves identifying all the materialized qubit that may potentially be used to answer the query, pruning the set of using knowledge of dominance relationship among the qubits, estimating the cost of using the remaining materialized qubit and selecting the qubit with the least cost. So, now which qubit I have to select, which material qubits I have to select. So, I have to select the qubit that gives me the less cost. You need to estimate what is the cost of using that qubit, and I need to select a qubit with the least cost. Let us take an OLAP query processing. Okay, so what we have to process? Let the query to be processed is on a brand and provenance or state. Which query I have to use? So, now here what I want to process, I want what type of a particular brand is sold in a particular state with the condition year 2004, and there are 4 materialized cubites available with me. Now, I want an information. What is my query? In the year 2004, which brand is sold in a particular state? And there are 4 materialized cubites available. One is year, item, name and city, this is already calculated. Second is year, brand and country, year, brand, provenance or state, item name, provenance or state. Which one I have to use? Which qubit I have to use? I have to use a qubit which give me the fast response and it has to cost me less. So, here which should be selected to process the query? Year, item and name and city. Here the provenance or state is not present and brand is also not present. Here year and brand is present, but directly country, state is not present. Here year is present, brand is present and state is present. Here item name, provenance or state is present. So, the only option left for me to use the materialized qubit year, brand, provenance or state. This is how I need to select the materialized qubit. Whenever a query is put in front of me, I need to check for the materialized qubit and I need to select the qubit which give me the proper answer with the least cost. Now, coming to the OLAP server architectures, that is ROLAP versus MOLAP versus HOLAP. What is ROLAP? Relational OLAP, relational online analytical processing. What is MOLAP? Multidimensional OLAP. And what is HOLAP? Hybrid OLAP. Logically, OLAP server present business users with multidimensional data from a data warehouse or data marts without concerns regarding how and where the data are stored. What is the purpose of the OLAP servers? The purpose of the OLAP server is to present business users with the multidimensional data from a data warehouses or data marts without concern regarding how or where the data are stored. However, the physical architecture and implementation of OLAP server must consider data storage issues. Implementation of data warehouse servers for OLAP processing include the following. First one is the relational OLAP, relational online analytical processing. ROLAP works directly with the relational database. The database and the dimension tables are stored as relational tables here. Now, what is relational? Directly it is giving an information. The database and the dimension tables are stored as relational tables and new tables are created to hold the aggregated information. It depends on a specialized schema design. So, the ROLAP method relies on manipulating the data stored in a relational database to give the appearance of a traditional OLAPs. And here slicing and dicing functionality can also be added and can be added. In essence, with each action of slicing and dicing is equivalent to adding where clause in the SQL statement. Slicing and dicing, slicing is cutting down and dicing is adding down is equivalent to where, adding a where query, where clause in the SQL statement. So, the ROLAP server or the ROLAP tools do not use pre-calculated data cube. Now, here what is happening? Here materialization we are not using. the partial materialization or full materialization will not come into picture. The rollup tools do not use pre-calculated data cubes, but instead they pose a query to the standard relational databases and it is stable in order to bring back the data required to the answer the question. So, here we are not going for materialization or we are not pre-calculating the data cube, but instead we are posing the query to the standard relational database directly in order to bring back the data required to answer the question. Rollup tool feature the ability to ask any question. Any query can be put to the rollup. Because why? Because here there is no limit to the content of a cube. Rollup also has the ability to drill down to the lowest level of detail in the database. That is the best advantage. Rollup also has the ability to drill down to the lowest level of detail in the database. Coming to the multidimensional OLAP or the MOLAP. MOLAP is the classic form of OLAP and is sometimes referred to as just OLAP also. Just OLAP is also nothing but a MOLAP, because always the data warehouse deals with the multidimensional data and there is no doubt in that. So, MOLAP can also be represented as OLAP, or OLAP is in simple terms you can just call it as OLAP. So, what is there in the MOLAP? So, MOLAP stores data in optimized multidimensional array storage. Now, here the difference comes. What is that? Here data is stored in an optimized multidimensional array storage rather than in relational database. In rollup, what we are doing? In rollup, we are storing the data in the form of a relational database. Now, in MOLAP we are storing the data in the form of optimized multidimensional array storage. So, therefore, the MOLAP requires pre-computation of the cuboid. In rollup, we are not pre-computing, but MOLAP requires pre-computation and the storage information in the cube, and this operation is known as processing. In the rollup, we do not require pre-computation of the data and we do not require the storage information. However, a multidimensional MOLAP requires pre-computation of the data or the cuboid, pre-computation of the cuboid, and also it requires storage information in the cube. MOLAP tool always generally utilize a pre-calculated data set referred to as a data cube, and this data cube contains all possible answers to a given range of questions. So, here materialization is done to the cuboid in a such a way that whatever answer, whatever a question comes to the cuboid, the answer is ready for it. The advantage of MOLAP tools over here is it is very fast response time. It has very fast response time and the ability to quickly write back data into the data set. That is what the advantage. What is the advantage? Very fast response time and the ability to quickly write back data into the data set. Next, coming to the HOLAP, hybrid OLAP. If we combine HOLAP and MOLAP, it will become hybrid OLAP. There is no clear agreement across the industry as what constitute the hybrid OLAP. So, there is no clear distinction which thing we call it as an hybrid OLAP, except that a database will divide data between the relational and specialized storage. For example, some vendors a HOLAP data will where some vendors say OLAP databases will use relational tables to hold the large quantities of detailed data and use specialized storage for at least some aspects of the smaller quantities of more aggregate or less detailed data. Relational tables to hold the data large quantities of to hold the larger quantities of detailed data is nothing but the rollup, and use specialized storage for at least some aspects of the smaller quantities of more aggregate or less detailed data, smaller. OLAP addresses the shortcomings of both MOLAP and ROLAP by combining the capabilities of both approaches. Now, OLAP is having the capabilities of both the things. It is having the capabilities of MOLAP also, and it is also having the capabilities of ROLAP. That only here it is being told that it uses relational database to hold the larger quantities of detailed data and use specialized storage for at least some aspects of the smaller quantities of more aggregate or less detailed data. So, the OLAP addresses the shortcomings of both MOLAP and ROLAP by combining the capabilities of both the approaches. For that only, OLAP tools can utilize both pre-calculated cubes and relational database sources. Now, let us take the comparison between the MOLAP and ROLAP. Now, here we are going to compare MOLAP and ROLAP with respect to the different properties. What are the properties over here? One is data structure, disk space, retrieval, scalability, for which it is suited for, and DBMS facility. Now, first take the data structure. MOLAP, multi-dimensional database using sparse arrays. Now, here the data is stored in the form of arrays, and here in MOLAP we have pre-computed data cubes. What is the data structure of ROLAP? Relational tables. Each cell is a row. MOLAP is a multi-dimensional database, whereas ROLAP is relational data table. That is the data structure. Next, coming to the disk space. Separate database for data cube, large for large data cube. So, now here we have a separate database for every data cube, and here we require large for large data cubes. But MOLAP requires a huge storage space, but ROLAP may not require any space other than that are available in the data warehouse. It does not require any space other than that are available in the data warehouse that are sufficient for the ROLAP servers. Now, retrieval, what is the response time? Fast. Why MOLAP is fast? Because here the data cubes are pre-computed, the values are already available. Whenever you put a query, immediately the results are available to you. But ROLAP, it is a slow, because we are just maintaining the data tables, relational data tables. Whenever you put a query, it has to compute on the fly, and it takes a time to get the answer for it. Now, scalability, limited. We cannot increase a huge size, but scalability in ROLAP is excellent, whereas in MOLAP it is limited. MOLAP is best suited for inexperienced users and limited set of queries, whereas ROLAP is best suited for experienced users and queries change frequency. DBMS facilities usually weak, and here DBMS facilities are very strong. So, with this we come to the end of this video lecture. So, in this video lecture we studied indexing of the OLAP data, how bitmap indexing is done, how join indexing is done. We have seen with an example also for all electronics data warehouse for the bitmap indexing as well as for join indexing, and we also seen the linkages between the sales fact table and the location and item dimension tables, and we are also seeing join index tables. Then we also studied efficient processing of the OLAP queries and what a query processing should follow, then how a OLAP query is processed, and we look on to the 3 different architecture of OLAP servers. One is ROLAP or MOLAP or HOLAP, or ROLAP is relational OLAP, MOLAP is multidimensional OLAP and hybrid OLAP, and finally we compared MOLAP and ROLAP with respect to the different properties like data structure, disk space, retrieval, scalability, and for which it is suited for, and the DBMS facilities. With this we come to the end of this video lecture. In the next video lecture we will go to the concepts of data mining. So, with this we end on this video lecture. Thank you one and all.